Hello, everybody. My name is Devkumar Banerjee. I'm at A&M Consolidated High School in College Station, Texas. And today I will be presenting on the benchmarking performance of machine learning algorithms for cluster computing. And so what exactly is machine learning, right? So it's a field of study that enables computers to essentially learn without being explicitly programmed to do so. And so it's a subset of another field of study called artificial intelligence. And artificial intelligence enables computers to perform tasks that generally require human intelligence. For example, let's say driving a car, writing stories, and so on. And so machine learning in and of itself is a behavioral model. It takes data as input and then pre-processes the data and then feeds it into a learning computing engine. And so this engine works recursively by minimizing error for a given set of constraints. And so this enables a predictive model to be generated. And so the following slide shows different types of machine learning algorithms. And the two schematics shown here are different examples of machine learning algorithms. And so now I'm going to go over a few popular open source machine learning frameworks. And so the first one is TensorFlow. It's a machine learning framework developed by Google, and it's been used by many companies as an industry standard for creating machine learning models. And it has quite an extensive documentation, and its flexibility has also contributed greatly to its popularity. The next framework is a version of TensorFlow that was built specifically for IoT, or Internet of Things, as well as smartphone devices. For example, let's say Raspberry Pi and generally smartphones. And so it's called TensorFlow Lite. And while it is faster than regular TensorFlow, it has slightly poorer accuracy and limited functionality, since it doesn't really allow you to train a model on low-powered hardware. And so the next framework is called PyTorch. And so it was developed by Meta, which was formerly Facebook, and it's used by many scientists in many fields of research for many AI ML applications. And so, like TensorFlow, it has quite an extensive documentation, and its flexibility has also contributed greatly to its adoption. And so this next framework is called PyTorch Lightning. It's open source and it's based off of PyTorch. Also, it automates a whole lot of that backend code that's required to build and run machine learning models on different hardware platforms. And so say you want to, you want to train a machine learning model both, at a supercomputer at like a university near you, as well as on a cluster that you built at home, right? You can do the same thing in two different places by changing less than 10 lines of code. And this has led to its popularity. And so the last framework I will be going over is called Horovod. And so it's an open source distributed training framework for computing clusters, which was developed by Uber. And so essentially it allows you to train a single machine learning model on many devices and many GPUs. So that makes it quite ideal for high performance computing clusters. And so one of my main motivations for this study is to implement machine learning in IoT, or Internet of Things. And so this requires that one can train machine learning models on affordable computers. For example, let's say the Raspberry Pi. And this will also have the side effect of promoting data science education and applications to those who would otherwise not be able to afford a computer, since the Raspberry Pi is it's a sub $50 priced computer. And so whenever you think of IoT, the Raspberry Pi always comes out as a huge contender. And that's because it has a large amount of system resources for a pretty low cost. And this gives it a sort of strength in numbers that we can use to create an affordable HPC cluster. However, there is one roadblock. That is the lack of machine learning support on the Raspberry Pi. TensorFlow dropped support for the Raspberry Pi with the release of TensorFlow Lite. However, cluster computing for IoT using the Raspberry Pi is still a huge possibility, since the Raspberry Pi offers access to open source HPC software on a sub $50 computer. And one example of open source HPC software is Slurm, which is the simple Linux utility for resource management, and it allows you to create a cluster of multiple Raspberry Pis. And in many universities, students and faculty use HPC clusters and supercomputers for things like numerical simulations and machine learning. So there are differences in training performances in clusters of varying sizes and with varying devices. For example, larger clusters have larger amounts of system resources, but at the same time, they're plagued by increasing network latency and slower response times as the devices that you're using to control the entire cluster have to manage more connections. And so in this study, the hardware that we're using is a single Raspberry Pi Model 3B Plus as our master node. This essentially controls 4 Raspberry Pi Model 4 4GB compute nodes. And so essentially, the master node will essentially dedicate which compute nodes are essentially doing which tasks in the machine learning model. And so for this cluster, you have a choice of either using a wireless or wired network interface. However, in both cases, it's quite highly recommended to assign static IP addresses to each Raspberry Pi. If you will be using an Ethernet interface, then not only will a network switch be required, but 5 Ethernet cables will also be required. Since we're using these Raspberry Pis for an AI ML use case, it's quite recommended to use heat sinks, since machine learning is quite resource intensive. And if you are not going to be using shared or network storage for hosting your source files, such as data and your training script, I recommend using a USB flash drive or other storage medium and setting up a network share on that. And so this slide details the various steps used to set up each node in the cluster. And so for our study, this is the first configuration for our network topology. Essentially, we have our single control node, which is the Raspberry Pi 3B+, which will interface to our worker computers using Slurm. So it will use PyTorch Lightning to train the model, and so PyTorch Lightning itself will scan whatever resources that Slurm allocates for it. And so Slurm, in this case, is our backend. And in each trial, the number of worker nodes will vary between 1, 2, and 4 nodes. And so our second configuration is quite similar to our first, except instead of using PyTorch Lightning to manage distributed training, to manage the entire distributed training process, we will use Horovod instead. And so for the past 2 decades, machine learning and deep learning has been quite a popular topic in fluid dynamics. And so one paper that was quite attractive when we were doing the study was using deep reinforcement learning for active flow control. And so at the time, this required considerable speedups for more challenging flow configurations. However, it did consistently reduce drag by applying active flow control after training using DRL. And so a similar model will be explored for this investigation. And so the authors of that paper refined the model both by adapting the DRL algorithm for parallelization and parallelizing the numerical simulation as well. And this is the model that we will be using in our study. And so this study's proposed methodology is to use the above models to benchmark the performance of these active flow control models by utilizing distributed training on 1, 2, and 4 node Raspberry Pi machine learning clusters. So in this case, when we talk about performance, we refer to the time used to train the model, not the model performance itself. And so while we're still doing the study, we expect to see that the 4-node cluster requires 4 times less time in the model benchmark than on the single node platform. Since while usually you see a trade-off in larger clusters since they have high network latencies, but in this case, since we're using smaller sized clusters of 1, 2, and 4 Raspberry Pis, this effect should be negligible. And so we've encountered quite a few setbacks while trying to run this study. And a big one is that TensorFlow dropped support for the Raspberry Pi, and this led to many setbacks while compiling newer versions. So compiling newer versions on your, like by myself, that didn't exactly work out. So while unofficial packages of TensorFlow did work on their own, the distributed learning package that we're using, Horovod, it requires an extension for TensorFlow. And so while this extension is available on basic laptops and desktops, it's not exactly available, by default for devices that aren't actually supported, like the Raspberry Pi. And so this requires these extensions to be compiled separately. However, after about 150 hours of troubleshooting and failing to compile the TensorFlow C library, I just ended up switching to PyTorch Lightning. And so while the distributed training functionality in our PyTorch Lightning training script is working so far, more work will be needed to refine the training script so that we may be able to apply it further to the Raspberry Pi cluster. And another setback is that while Horovod lists itself as being compatible with PyTorch Lightning, the documentation for using both Horovod and PyTorch Lightning is obsolete. And so some challenges this study presents include how can we automate this process of training on a Slurm cluster? Does performance really vary when using uniform clusters of devices that are not Raspberry Pis? For example, if we were to create another cluster of a group of the same laptops, for example. If we have 5 of the same laptop, put them in a Slurm cluster, how will model performance vary? And how does model performance vary when using devices with varying resources in a single cluster? So let's say if I were to take a server and put that in a cluster with a single desktop computer, how would model performance vary then? And also, finally, how severe an effect does network latency and stability have on cluster performance? With that, I would like to end this presentation by acknowledging the NASA and TFAWS organizers. I would like to acknowledge Dr. Dilma de Silva, who was formerly at Texas A&M University, who is now a division director at NSF's Computing and Communication Foundation. I would also like to acknowledge Dr. Dhruv Chakraborty, who is at the High Performance Research Computing Center at Texas A&M University. I would also like to acknowledge Mr. Mickey Bird of Bird Academy in College Station, and Mr. Garrett Mills, who is currently a graduate student at the University of Kansas. I would like to actually acknowledge Mr. Mills in particular because I think back in 2019, he had released a blog post detailing how to get a Slurm cluster running on the Raspberry Pi. And this blog post helped me quite a bit in setting up the various prerequisites for this study.